Hello everyone, welcome back. So far what you have learned theoretically is enough for you to tackle the final project of the NLP portion of the NLP and MLOps workshop. In this video, we're going to do a very quick recap on the first surge of deep learning in NLP, and afterwards we're going to talk about the second surge of deep learning in natural language processing. Okay, let's do a quick recap of what you have learned so far about deep learning in natural language processing. So here are some of the key points. You know the benefit of deep learning in NLP. You know about RNNs, how they came to be, and neural network-based language modeling. You know the key NLP deep architectures and their corresponding equations. Some of the causes of vanishing and exploding gradients. Some solutions to vanishing and exploding gradients. The issue of long-distance dependency in NLP, which is a prominent one. Some solutions to the long-distance dependency issue. You know about representation learning. You know about deep versus shallow networks in natural language processing. And you know about the advantage and disadvantage of deep and shallow networks. We have not solved completely yet, however, is the issue of long-distance dependency. Consider the task of machine translation, for example. You can have an input sequence, a source sequence, and you can have a target sequence in different languages. At the time of generating in the target language, let's say you're translating from English to French. At each point in time when you're generating your French utterance, you may pay attention to different parts of your English source utterance. It is a long distance dependency issue because at each point in time, some parts of the source language may become more prominent, particularly the part that you think you need to translate at a certain time. So in addition to gates, another solution to the issue of long distance dependency is the attention mechanism. Let's take a quick look at this graph and then we jump towards the equations in the next page. So let's think about the issue as a machine translation issue, for example. Let's say this is your source sequence on the left side, and on the right side, let's think of this part as your target sequence. As you have seen before, recurrent neural nets, similar to humans, generate words one at a time. Okay, let's pause the video and guess what type of architecture this architecture would be if you have a recurrent network that processes a source language that you want to translate from, and then you have another recurrent network that would generate the translation in a different language. All right, I assume you have paused the video and by now you have the answer. Yes, it's a encoder-decoder architecture. So the encoder's job is to come up with an understanding of what the source language tries to achieve, what the meaning of the utterance in the source language is, pass that over to the decoder, and the decoder is tasked with generating the natural language in the target language. This is not a trivial task at all. You can see lots of different errors, from generating the same word over and over again when they fall into the local optima, generating a phrase over and over, to ungrammatical utterances, so on and so forth. And all of them do rely on long distance dependency. Or better said, an understanding of long distance dependencies. If you have that understanding, you are more likely to generate a grammatical utterance in the target language. You're also um, more likely to capture the patterns in the source language in order to translate them. All right, so what is this image showing us? Basically, you have two layers of your recurrent neural net. Do not be distracted by the arrows at this point, and forget about the right side. Forget about the decoder for now. Okay, so I have two layers of encoder, and each one has a hidden state, right? Okay, so these hidden states, remember, they represent a sequence. So this hidden state, for example, does not only capture the representation for the present input word, but it has the previous words indirectly through the hidden state information carried over to. Okay, so that's that. Now let's talk about the arrows, for example, and at this point just forget about these. So this part of the graph. Okay, just your ordinary LSTM. It just has two layers. On the other side, you see the arrows are going left. So the right side you get, so you have some hidden states. Instead of getting words, the second layer, instead of getting words, they just get the hidden states. The previous layer, they start with that. They go from left to right. The right to left, it has been shown, sorry, over and over again, that if you have a bi-directional LSTM, something like this, so you can start right to left. It's like speaking in reverse order a language. Or understanding a language, reading from right to left. If English is left to right, for example, you can read it from right to left. It has been shown that this architecture helps the performance, having both directions at the same time as opposed to just one direction. And the reason of that is kind of apparent. Um, One potential factor that can contribute to this extra performance is the fact that you have if it's a long sequence, you go from left all the way to the right. Even with gates, the ones at the start of the sequence are prone to be forgotten by the time you get to the end, right? Because information keeps coming in, right? And when you go right to left, maybe the first item on the right is prone to be forgotten. When you have these two, you have kind of both representation. More accurately, if I want to say, is in this sequence, you kind of see the dependencies of, when you're going left to right, you kind of see the dependencies of items left to right. So you kind of see how the hidden state of t minus 1 affects t, but you don't really see how t plus 1 affects t, right? And true, language is generated in a linear manner, but it doesn't mean that the next word you generate does not change the meaning of the previous word you mentioned at the time of understanding, right? So, and again, I have to clarify more accurately. Usually, when you have bi LSTMs, you run them directly on the words, right? Not like this. This one is saying that, oh, I get the hidden states and then run left to right on the hidden states that come right to left, right? I mean, you can do that as well, but usually what happens is that the left to right LSTM and the right to left LSTM, they both run on the words directly, right? I mean, you can still, this architecture is still viable. You can still have add one layer right to left, add one layer left to right. But regardless, now, so that's why I was mentioning you don't need to be distracted by these arrows, and you don't have to do a bi-LSTM, a bi-directional LSTM. You can just do unidirectional LSTM with only one hidden state. And only when you want to improve, then you can, of course, use more complicated architectures. All right, so that's that. And on the generation side, we see that it's both left to right. Okay, so regardless of what it is, you get your hidden states, right? As previously um, seen, both during reading the source. Just think of it as, again, think of it as a machine translation, reading the source language, as well as when trying to generate the target language. Okay, so you have all these hidden states. What attention does is nothing but actually weighting higher certain words in the sequence at a certain time t. That's why there's a t. So attention is shown sometimes by a, sometimes by alpha, um, and it says attention at time t. How much should I weight? And you can think of weights as coefficients applied to the entire vector over here. So you have a vector here, you have a vector here, you have a vector here. If this attention is saying at time t, I want to generate this y, let's say I want to say, I don't know, the equivalent of truck in French, then let's say this word is truck, this word is drove, and this word is I in English. You obviously want to pay attention to the truck English word when you want to generate the sort of French equivalent, right? So you want to have this representation, this word representation, truck's word representation, weighted higher. If you have a few vectors, you're combining them linearly, right? And one of them, let's say you're adding them, just for the sake of the argument, and one of them has a higher coefficient, what's going to happen? Pause the video and figure it out. Okay, I assume you've paused the video and by now you know the answer. Basically, the angle of this video is going to take over, right? So it's going to take every other vector towards its own direction. In other words, most of the meaning of the utterance will be governed by the meaning of this word, right, if you add them up. But regardless, the attention part just tells you, oh, I want to pay this much attention to this guy, this much less attention to this guy, and much less attention to this guy, for example. Okay, and then we have a context vector. The context vector is basically the summation of your attention, which is the coefficient, and your hidden states, right? The context vector at time t is your attention at time t. You see your attention at time t is paying attention to all of them in different degrees. So basically, you just multiply your AT by this H, multiply your corresponding AT by this weight and this weight, right? And then just sum them up, right? So this AT for each of these hidden states is nothing but a probability, right? A value between 0 and 1. So you multiply this guy with a value between 0 and 1, same here, right? So this AT is an entire sort of vector of coefficients, right? Each coefficient is applied to one of these hidden states. Okay, there your context vector is only passed to the decoder. So the decoder doesn't need to have all of these guys separately. Basically, you just sum them up using attention, and this will, your C at time t, your context vector at time t, represents the most important bits of information at time t for generation of the word y. All right. So that's what attention is. We have various types of attentions, but in a nutshell, that's what attention does in every scenario. Okay, by now the equations must be very simple for you. Basically, your EIT is your alignment score, alignment between your target and your source word. If you're thinking about a machine translation task, you can think about multiple tasks, but let's focus on one for now. Your V transpose is just a vector. You'll see its importance in a second. Um, within the parentheses, you have your HI, your hidden state I. So you see that there's a superscript and a subscript here. The superscript T is referring to the generation time T, right? You want to output, for example, Y at time T, right? You're trying to figure out what Y should be, what word should it be. Okay. So T refers to the decoder time step, and then I refers to the encoder time step. So which word are we talking about? Which hidden state are we talking about? Okay. Basically, you have your weight matrix for your hidden state I. You have your weight matrix for your hidden state S at time T. Yes, hidden. So H refers to the encoder state, and S refers to the decoder state. Decoder state. Okay, and each one has its own weight. All right, weight matrix. Okay, you multiply these two, and by the weight matrices, and you add them together, and you add your bias. Okay, very simple. So linear equation, right? And you apply 10H on it, right? So when you apply 10H on it, you kind of compress the values between -1 and 1, right? So that's what's happened so far, and then you multiply that by a VT because you got a vector. So this is a matrix by vector is a vector, matrix by vector is a vector, and your bias gets broadcast, so it's still a vector. And then that's why you have V transpose, because you want to have another vector of the same size that when you take the dot product of the two, you get a score. You get a score. Your tan H again just shrinks the values between the vector values between -1 and 1. Okay, so you get one score. You get one single, and everything over here is trainable, right? Okay, it's already being trained. Okay, so basically you get for a word I or a state I, better said, because it's not just one word. Remember, it's an LSTM. You may have history information transferred into the state I. You have hidden state I, and you have your hidden state T, right? And then this score ETI tells you how related they are. Again, how related the state T is to the hidden state I. Let's say this one is I, for example. Okay, how related they are. And it's a score, right? It's not a probability, it's a score. Okay, all right. So basically, the next step would be to capture the softmax, right? And you see that it's referring to AET, so this is a vector. You want to get a softmax of it, right? So softmax all the values. Now you're trying to create probabilities for all of the i's in here, for all of the hidden states, right? So you apply softmax to it, basically for each I, for each hidden state, you exponentiate it, and you divide it by the sum of all the scores for i's in the um, encoder hidden space, right? All the hidden states of the encoder, all of them, and each one has a EIT associated with it. You just sum them all up, right? At time step t. Okay, you sum them all up, and then in the numerator you have your score for one of these hidden states. Right? So each one will be now a probability. That's alpha, right? That's your That's your kind of specific uh, probability or specific attention score for a certain hidden state at time step t, right? So we show that by alpha, um, and your entire attention vector is called at. Okay, beautiful. So you have your attention, and now all you need to do is to, for each hidden state, the encoder time, you need to multiply it by its coefficient, aij. So each hidden state j, um, you just multiply it by its relevant coefficient. Okay, and you get your context. Well, and you sum them all up, and then you get your context vector for time step t. So these equations, these two last equations, the indices are kind of mixed up. What's actually happening? Consider I to be t. So I is referring to the time step t, um, only for these two equations, and j is referring to your hidden state I, right? Um, so a specific hidden state, and then for the rest of hidden states, you're exponentiating and summing them up, right? So this is your alpha IT, as you saw before, um, and this is your, and you see in the image, and this is your CT, context, um, uh, your context vector T, right? So again, these two equations are good. Your alignment score is good. It's I and T. T refers to decoder. T refers to the decoder time step, and then I refers to the encoder time step. And similarly for your attention, it's the entire um, alignment score for all of the encoder states at time step t. And over here, these last two equations, this is CT, this is CT. Basically, replace in these two equations, replace any I with a T and any J with an I, and then all of these equations relate to each other. Okay. Anyhow, so you get your context vector T by multiplying the attention for each hidden state and by its hidden state. Um, so that's your here you have it. That's your entire context. So this context is an attended over representation of the entire um, sequence. So you can see that because we take into account both the decoder and the encoder, um, it's a good representative of both states, your context vector. And then you can pass it along to your context vector um, is used to make the final prediction at time step t. So as stated earlier, the version of attention that you saw in the previous slide um, basically relates the decoder to encoder, right? So it's attending over the encoder states, given the information in the decoder states. But a lot of times, what happens in NLP, especially in generating natural language, um, you may have good context for your encoder, but you still end up repeating a phrase, repeating a word. That's because your network is not aware, it's not perfectly aware of what it's, or optimally aware of what it has generated before, right? So one remedy to that issue is to have a mechanism called intra-attention, or also referred to sometimes as self-attention. Right? Let's use intra-attention because and preserve self-attention for a slightly different sort of use. Okay, so in intra-attention, basically, you're referring if I go back to our um, neural network, your intra-attention would only observe the decoder sequence. The decoder sequence. It won't look at in any way the hidden states of the encoder. Only the decoder. And at time t, it just takes a look at the previous ones and pays attention to specific ones to capture the grammatical patterns only within the target language. And it's important. All right. So okay, so if you do that, you can see very interesting patterns. So here we're using self-attention to highlight the words that matter. All right, so what's happening here? Basically, at each line, you're looking at one word. So the first line you're looking at you're at time step T, your first word, and the second line you're looking at FBI as your time step T, and third line is, fourth line chasing, fifth line A, sixth criminal, so on and so forth. And the items that are brighter, um, they just have a high attention on them, right? So again, it's inter-attention. The mechanism and the equations are very similar um, to our inner attention, but um, but it only considers the target sequence. Okay, so let's see. It's interesting. So during time step da, obviously you don't have access to any other history words, so you haven't generated anything else to pay attention to. So nothing's happening here. When you go to FBI, however, you see that at the time of generating, it can be generating or reading, but let's think about it as generating. FBI, your network pays attention to da, right? And then at time of is, it pays attention to FBI. You can see there is a verb agreement there to consider. And then when you see chasing, when you're looking at chasing or generating chasing, you see that your model is paying attention to FBI as well as your subject as well as your verb to agree with, right? Um, and and when you look at A, looks at chasing, and when you look at criminal, looks at is and A. Very interesting. And when you look at on, you don't see a lot of dependencies. It's a function word, so um, this on really doesn't depend on anything else. It is part of this phrase on the run, which is a kind of a collocation of three words. And then you have your um, uh, it's for some reason to on is. And during the run, it's interesting, you're paying some attention to on so it recognizes that pattern. And FBI chasing a criminal on the run. You see some spread of attention, and um, at the time of full stop, you're seeing chasing, criminal, and run. Okay, anyhow, you can visualize your attention. Um, Sometimes it directly makes sense to you, sometimes it doesn't. It's one way to try to justify and reason about the output of your neural network. So what is it my neural network pay attention to, when making such and such decision? Right now, the decision is choosing a word, but the decision could be, predicting a risk, could be um, predicting or some sort of behavior, some sort of action, or predicting a response. What's the response? Let's say it's a conversational agent. What response should I give? Or what should I summarize? So attention helps you understand what your neural network is doing at the time of making a decision. Okay, so the equations are very similar. Throughout the equations, you can ignore D. D is basically referring to the decoder. That's fairly obvious. You have your T and your T prime. Basically, your T is referring to your present time step, and T prime is referring to any other time steps, right? Any other, say, hidden state. Here, H is your hidden state for the present time step. Okay, for your decoder, all right, and you transpose it similar to that V in the previous equation. You just want to have, you want to be able to do a dot product. And your W is your decoder weight matrix, right, for the attention, right, specifically for the attention mechanism. And then your H2 prime is any other word you're trying to score, right? And just as before, you get a scalar. That's your E, that's your alignment score. And then very similarly, you exponentiate them and will exponentiate your ETT prime, and then you sum every other, you sum all the ET, ATJs in your sequence. So you sum up everything else, right? It's interesting to pay attention to the fact that it goes from your J goes from 1 up to T minus 1. So you don't look at, when you sum this up, you don't look at obviously time step T. You don't look at T plus time steps, right? So you look at only the sequence that has been already generated, right? The sequence has been already generated, or before a word, is your entire is every other word that you want to compute attention for, right? Um, and and that's how you compute attention per a word in the sequence. All right, so once again, you're only looking at the words that are before T, that have occurred before time step T. That's the set of your T prime variability, as well as your J, right? So you're only looking at the words before T. And here you exponentiate your alignment score for a specific T prime, for a specific word in the sequence before T. And here's every other T prime, including the one you computed in the numerator, and you sum them all up to get probabilities, right? It's very simple. You get your alpha, and then you get your context vector at time t, again by just computing the weighted linear combination of hidden representations, right? Using this alpha, right? Very simple. All right, so far you know two of the most prominent attention mechanisms that are used in various recurrent neural architectures, including the famous long short-term memory LSTM architecture. But there are other types of attention. There is hard attention and soft attention. Okay, so soft attention is easy. Basically, both inner and intra-attention that you've learned so far are examples of soft attention. Use your softmax. It's differentiable. You can compute the gradients, and everything is trainable. And you basically look at everything else. Either if you're looking at only the decoder sequence, for example, you look at every word before time step T. If you're looking at everything, both decoder and encoder, you're looking at everything in the encoder, every state in the encoder, and compute the softmax. All right, so that's soft attention. and you know it very well so by now. How about heart attention? So heart attention picks out a specific item only. It picks out a specific item only, and only highlights that. So it's easier to compute. Basically, you just predict one word in the sequence. For example, if it's a sequence to sequence model, as you've seen so far. But the issue, and so you don't have to look at everything else, right? You don't have to look at everything else and compute the cost of softmax. But the issue is that it's non-differentiable. So you have to use some alternative methods than rather than graded descent to train it. You can use usually people use reinforcement learning methods, which is beyond the scope of this course. So another one is easy. So it's global. So when people talk about global attention, they're talking about soft attention. So your soft attention looks at everything. So it is global. Your local attention, however, can is kind of a hybrid between hard and soft attention. You can still pick only a small window if you're talking local attention. And more accurately, in fact, you pick one item in a sequence, and then you have a window that computes attention over that window, right? So you don't have to go through the entire sequence, you just compute attention over a small window. So in local attention, your attention scores as well as your context vector are not at time t are not dependent on every time step. They just look in a small window. They're just looking at a small window. So you predict one item in the sequence and look at a window, let's say a window of size, 1 on each side. So you get these three and you compute the context vector from these three, which is kind of faster and does have some, um, um, does have some context, and it is trainable and differentiable. So that's why it's called hybrid, because it's local. It's looking at a specific um, you know location, similar to hard attention, but it also has some context information, and it is differentiable. So that's in that regard, it's kind of similar to soft attention. All right, so with that, you learned almost all sorts of attention that exist, aside from one that you'll learn in a future video. Um, and you can use these attention mechanisms to improve the performance of your models. Remember that when you're working on your project and you try, the first approaches. You don't have to go all the way and create the most complex method to begin with. You begin with a simpler, method, and then move on towards a more complex one. But if you use a simpler method and you see that, oh, okay, I can still improve the performance of the model, then attention is definitely something you want to try. And I would say definitely try, your inter-attention. So when you pay attention, the context vector represents the source, and given the decoder time step, as well as intra-attention. Intra-attention is important both within the source itself and especially within the decoder. So both within encoder and within decoder, and especially within decoder, intra-attention can really help generate better results, especially if you're generating natural language. All right, with that, I'll see you in the next video.